All right, good morning, chemists. We'll get started. So plan of attack for today is to just do a little bit of chapter 19. There's a good stopping point in a couple of slides, wrap up our idea of the second law of thermodynamics and entropy change of the universe. And then we'll move on to midterm 3 review. We'll spend the majority of the class, like 60 minutes on that. Got a couple demos to reinforce some ideas of solubility, but we'll have to wait and get through a little bit of chapter 19 to finish up the topic of entropy and all of that. So, entropy. We, last class, talked about what it is. We calculated entropy change of the universe for some spontaneous processes. Let's remind ourselves, for a spontaneous process, a process that happens on its own in the given condition, once it gets going, we are looking for an entropy change of the universe to be what kind of number? Positive. That is what the second law of thermodynamics says, that any reaction or any process, any change is spontaneous if entropy change of the universe is positive. Remind yourself that the universe means your system, so your reaction, and the surroundings. So we got to consider both. So we did some calculations for some processes, and then we looked at the particle view, kind of the significance of what entropy is based upon some different factors that we looked at here. So we can compare the relative entropies of substances based upon their microstates available for that system. So number of microstates increases for all of these different factors, volume, temperature. Those are common if it's like the same sample just in different conditions. But also number of molecules. If you shove more particles in the same space, there's going to be more microstates because there's more possible, like statistically, more places to put a more number of objects. But also we saw that complexity of our molecules also contribute to absolute entropy of our samples. So I mentioned, we can have a gas sample. Gases, they bounce around like crazy idiots in a container. So if we think about those particles bouncing around, if your particle can not only bounce, but also bounce and wiggle at the same time, you introduce more entropy into that sample. So more bonds means more vibrations, more wiggling. And then molar mass, heavier things have more entropy, and then finally phases. So, we just looked at, pick the higher of the pairs of these samples. So in this example, we're just looking at the absolute entropy of these objects. That water at this temperature has some degree of entropy. Water at this temperature has some degree of entropy. This one has more entropy. So this is a common exam-like question. It's very easy to write one where it's just like pull-down menu where you choose which one has more entropy. And we include those factors. What's also common for an exam question is predict the sign of the entropy change of a reaction. So we're using the exact same skills, but we're looking to see, okay, how is entropy changing in the course of reactants to products? And we were thinking, okay, is the entropy change increasing or is it decreasing? So we have to look at both sides of the reaction. So here are some tips. It's still the same things, but there's we're not really changing temperature, so the common factors that we're going to look at is look at the states of matter of substances. Gases have the most entropy, like always. They always have the most entropy. If you just think about it on a particle view, like gases, they're bouncing around like crazy idiots, but solids, they just are very boring, very low entropy. So states of matter will help you decide whether entropy is increasing or decreasing, but also a common thing to look at is look at the number of moles of gas in your sample. Decide, okay, is my sample gaining moles of gas or losing moles of gas? Remember, number of particles was a factor in entropy. So if you're gaining more moles of gas, entropy is increasing. Though if you're combining gas particles to make less particles, then your entropy is decreasing. So let's see if we can't predict the sign of entropy for these reactions. So for the first one, we're going from a solid to a gas. What do we think? Increasing, yes. Solid, very boring. Gas, Crazy. All right. Calcium oxide solid plus a gas gives us one solid. What do we think? Negative. Yeah. So the giveaway here is that there's 1 mole of gas on the reactant side, and it's going to 0 moles of gas on the product side. Or you can think 2 particles on one side, 1 on the other. So there's a lot of indications that this reaction is decreasing its entropy. All right, the next one. Positive or negative? Negative. 2 gases to no gases. The next one. So you got, yeah, it's also negative. So count all of them up. So on the reactant side, I have 3 gases, 3 moles of gases, versus the product side, only 2 moles of gas. All right, so this one is also negative. All right, I added some sodium chloride solid to aqueous, so we are dissolving salt. Think about on a particle level what that looks like, and think about, if you think about entropy as being disorder, that's fine. But what do we think here? Entropy is positive, increasing, yes. So in the solid phase, particles have no translational motion at all. They're just sitting there vibrating. But in the aqueous phase, the cations and anions are actually floating around. Yeah. Okay, CO2 gas to aqueous. It is negative, very good. Yes, because you might think in both of those, oh, you know, the particles are floating around, but in the gas phase, CO2 gas is confined to the entire container, versus in the aqueous phase, CO2 gas is just confined to the water itself, the actual liquid. So we're basically reducing that volume here. So this one is negative. All right, so those last 2 slides very similar to one another. Again, common exam questions. They're very easy to write, predicting the sign. And that's what we're going to do a lot of in this, these couple slides, is predict, you know, some information about a reaction that you might not have thought of previously. We're going to go into an insane amount of detail about some of these reactions and think about their spontaneity. Okay. So we looked at the particle view, conceptually what entropy is, so let's go back to math for a little bit. But thankfully, this isn't new information. We can, yes, predict the sign of delta S for a reaction, right, by just using concepts. But we can also calculate the entropy change for a reaction by doing products minus reactants. Does that sound familiar? Yeah. So remember in 1210, has enthalpy of formations. I think it's Appendix C, I think, in your textbook, has all that thermodynamic data. It had delta H's that you would look up, the delta H of formations, and you do products minus reactants, the stoichiometry. So I don't know if you remember from 1210, I told you just ignore the other columns. Just look at delta H, ignore the other columns. Well, finally, we are going to talk about those other columns, but thankfully, the calculations are the exact same. We can calculate entropy change of a reaction by using those entropy values for those same substances. So again, so like Appendix C, you'll find entropy values right next to your formation values for different substances. So our strategy to calculate the entropy change of this reaction, literally the exact same, just use entropy values instead. Note that entropy has a unit of Joule Kelvin. In the tables, these are still per mole amount. So we call these molar molar entropies. So that means we have to take into account the stoichiometry that is here. 1 mole of ammonia has an entropy of 190, but in this reaction, we are reacting 2 moles of ammonia, so we have to take into account that, right? So the process here is just do products minus reactants, be sure that you use the correct sign, you use the correct state, and you use those coefficients. I like to take inventory of things. I like to sum up both the reactants and product side and then separately and then subtract them at the end because I always mess up my negative signs. So if we look at our product side here, the entropy of the products is 2 times 192.5 joule mole Kelvin. And that's because there's 2 moles there. So that's my product side. Then my reactant side is 1 mole of nitrogen, so 191.5 plus 3 times 130.6. Again, that's all joule mole Kelvin. So each of those sides, sum them up. And so to get the delta S of this reaction, system is the same as reaction. As a chemist, our system is the reaction at play. Delta S of our reaction is the sum of each of those sides. Did I do this? I don't know. So products minus reactants, use the stoichiometry. What's nice about entropies is they are always positive numbers, because that is the 3rd law of thermodynamics, which we'll talk about next week. Okay, so there is the product side, minus 191.5 plus 3 times 130.6. We see, subtract 583.3. And so we get the delta S of this reaction is, I have it down here, negative 198.3 joule Kelvin. All right, so we see entropy is decreasing. The number of microstates in the course of this reaction is decreasing. Would you have predicted that anyway for this reaction? Yes, because we went from 4 moles of gas to 2 moles of gas. So the sign of this reaction does make sense. Very good. All right. Okay, so that is not new. So do take some time and look at Appendix C and just see all those entropy values that are given in Appendix C. So Appendix C, what you'll see are 3 different columns. The first column you have used before. Delta H is of formation. You've done that. You'll see another column that's delta G of formation. We'll get to that next week. And then the last column are entropies. Note that the units are slightly different for them. Delta H of formation is in the unit kilojoule per mole. So is delta G is in kilojoule per mole. But delta S has a different unit. It's joule mole Kelvin. So a little bit different. So do keep that in mind. Joules, entropies are typically given in a joule amount because they're typically small, but delta H's and delta G's are big energy values, so they're typically given in kilojoules. So keep that in mind when doing some of the equations that we'll do in a little bit. All right, so let's do one more. You know this reaction, right? Hydrogen plus oxygen, boom, make water, right? I didn't order that demo because I want more time for doing review, but I'll do this demo next week and compare it to another kind of explodey demo. But let's calculate the entropy change for this reaction as well. So remember, system means reaction for chemists. So we're just doing products minus reactants again. I've even highlighted them for you here. Do make sure you're using the right state. Here it's water liquid, so entropy change of the reaction would be a little bit different if this was gas was a product. So we got 69.9 there. This side of the reaction is 130.6 plus half a mole of oxygen, so 202 or 205, whatever. Right, so then delta S of this reaction is equal to 69.9 minus that whole sum, whatever that is. 130.6 plus half of 205 is 233.1. And so we get that the delta S of this reaction is negative 162.2 joule Kelvin. So we got another negative entropy. Look at the reaction. Would you predict a negative entropy change for this reaction? Yes. Moles of gas are going down again. Okay, perfect. Now, what other information can we gather from this question or from this information? Right? So yes, you can do products minus reactants and get information about entropy changes about this reaction, but let's dive in deeper about explaining the phenomena of spontaneous reaction. So first, let's think about this. Does this reaction happen in this room? If I had the hydrogen balloon right now, can it happen? So if it didn't happen, that means I could never light the balloon. No amount of candle lighting, nothing would happen. So tell me, when I do the hydrogen balloon experiment, does something happen? It does. So that means this reaction is spontaneous at these conditions, okay? There's a little bit of an activation energy that I have to get over, and that's what I use the little, the candle to initiate the reaction. But once it goes, okay? So this reaction is spontaneous at room temperature, at these conditions. This reaction is spontaneous. So that's this follow-up question. I want us to answer kind of more information about this reaction. It is spontaneous, this reaction at room temperature, once I get it going, right? Once I initiate it, it just goes off. I don't have to keep fueling the reaction to get it going once I get it started, right? So based upon that and what we learned on Tuesday, if this is a spontaneous reaction, what is the sign of delta S of the universe? Positive, perfect. Okay, let's put all of this information together. I know that delta S of the universe has to be a positive number. We just calculated delta S of the system, of the reaction. But we see here that, oh, this is a negative number, all right? We just calculate, or not surrounding, sorry, that's the wrong thing. System right there, all right? We just calculated that this reaction actually decreases its entropy based upon the balanced chemical equation. But if we know that this reaction is spontaneous at room temperature, there's this missing piece because those signs don't match, all right? So what does that mean that delta S of the surroundings has to be in order for this reaction to be spontaneous and match our observations? Delta S of the surroundings must be a positive number, a big positive number, all right? So we can make up for that negative decreasing of entropy of our reaction as long as our surroundings are increasing its entropy overall, right? So that's the only way to make this reaction spontaneous, if delta S of the surroundings is positive. So delta S surroundings has to be a positive number, has to. So yeah, we can counteract that negative value by adding a big positive number to it to make entropy of the universe positive overall. So let's, okay, so sure, entropy change of the surroundings is positive, so what? So that's where we use this last equation, where we can actually relate the entropy change of the surroundings to the enthalpy of the reaction, right? So think about it this way. If our a way we can increase the entropy of our surroundings is by heating it up, right? Heating stuff up increases entropy. So if I have an exothermic reaction, exothermic reactions release heat, therefore increase the entropy of the surroundings. So that's why the surroundings is equal to the opposite sign of delta H of the enthalpy of the reaction, because there's this heat transfer. Heat is being lost by the reaction, gained by the surroundings. That's the first law of thermodynamics. Hopefully that sounds familiar. So with this equation and transfer of heat between system and surroundings, what must the sign of this reaction be? It has to be negative, right? Because if I have an exothermic reaction, in the numerator it's a negative value, and negative times the negative is a positive, right? So this is an exothermic reaction. Is that consistent with your observations of life? Yes. The hydrogen balloon demo is highly exothermic, and it's also spontaneous because of this logic that we used to utilize the second law of thermodynamics. The only way this reaction is spontaneous, in order for delta S of the universe to be a positive number, the reaction has to be highly exothermic to counteract the negative entropy decrease of that reaction, all right? So this is how we've proved that the entropy change of, that this reaction is spontaneous at room temperature at these regular conditions, because delta S of the universe is positive. All right, so hopefully I didn't ruin the reaction for you. All of this is happening in the background, whether you like it or not. I know we enjoy it. We enjoy the exothermic nature of it, but all of it comes together, and we can explain numerically and using thermodynamics why this reaction happens at all. Okay, so let's do one more kind of inspection using logic to figure out, okay, what are the details we can pull out of a reaction if a reaction's spontaneous. Okay, let's look at this reaction. Okay, there's two kind of factors going on here. I have 5 particles on this side, 10 particles on this side. So how does the number of particles change delta S? It usually means that delta S what? Increases, is a positive number, right? It's a positive number. But look a little bit more closely. All right, yes, particles are changing, but there's some other factors that are changing here too. Isn't particle complexity changing? Yeah, look at one of those reactants. How many bonds are there that can vibrate? There's 5, right? There's 5 different bonds that can vibrate and wiggle. Versus on the product side, look at one of those products. How much wiggling can that product do? Just 2 bonds are wiggling. So how does molecular complexity affect entropy of a reaction? Usually that decreases entropy, doesn't it? So the question is, well, which one wins? Which one is the more important factor? This reaction has to either have a positive or a negative entropy change, or 0, but it's not. It has to be positive or negative. So which one is the more important factor? We can logic our way through this. All right, okay, so let's do it. So basically the moral of the story, let's figure out, is the entropy change of this reaction positive or negative, because it's not quite clear. Again, we're gonna logic our way through this. And we're gonna, again, utilize the second law of thermodynamics. Our goal is to get a positive value of delta S of the universe out. So let's ask ourselves, this reaction, when it happens, is it endo or exothermic? I promise you, you know what it is. Think about what's happening in this reaction. What are we doing? How do we go from products to, or reactants to products? We break stuff. Are we doing any forming? Nope. So this reaction must be endothermic. So the sign of delta H in this reaction must be positive, because all we are doing is breaking. We are doing no making, just all breaking. Okay, so this question is just like the previous one, just we're working backwards. If delta H of the reaction is positive, it's endothermic. It needs energy to move forward, so it's going to take it from the surroundings. What is the sign of delta S of the surroundings then? Negative, yeah, so delta S of my surroundings is negative because of this relationship, okay, heat transfer. So again, we're utilizing the second law. I'm telling you this reaction is spontaneous at like room temperature or whatever. Our goal is to get a positive value of delta S of the universe. We just deduced that delta S of the surroundings is a negative number. So what must the sign of delta S of the reaction be? Positive, must be a big positive number, because a big positive number plus a little negative number is still a positive number. So that means delta S of my system is actually positive. And we were able to deduce that by we didn't look up a dang thing. Okay, so based upon our answer we just got, we were able to figure out that this reaction's entropy is actually increasing. So what does that mean? Which factor was the more important factor? Number of particles increasing or complexity decreasing? It is particles increasing. That's the more important factor, because that matches what we just came up with. Number of particles increasing would indicate that entropy increases, while molecular complexity decreasing, we would assume, okay, entropy decreases. So we see that the number of particles increasing is the more important factor, because it matches with our conclusion that entropy of this reaction is actually increasing. All right, so I hope you feel a little bit smarter looking at reactions from like a really intricate and specific way to determine if they're spontaneous or not. I will point out, it is annoying to constantly balance system and surroundings. I don't like that. System and surroundings, that is the universe. I don't like to look at the entire universe. So as chemists, we like to focus on the reaction at play, and that's what the next part of this chapter is. It's another way for us to predict spontaneity, but in an easier way. We're gonna use Gibbs free energy, so delta G, to predict spontaneity. Back in the previous slides, we were always looking for a positive delta S of the universe to get spontaneous reactions. But when we use Gibbs free energy, we are actually looking for negative Gibbs free energy. So in Gibbs free energy, for a reaction decreases, that reaction is spontaneous. But here's the thing, this is still the second law of thermodynamics, but it's easier. Because if you look at the delta G reaction, look at all the subscripts. Delta G reaction, delta H reaction, delta S reaction. Everything is in terms of the reaction. I don't actually have to think about the surroundings. Okay, I can put everything in terms of the reaction, and then calculations become easier. But it's just another way to predict spontaneity. Okay, so we'll do that next week, and then I'll blow some more stuff up. Okay, so let's switch gears to midterm 3 review. All right, so if you haven't grabbed this document, it's right here. It's go.osu.edu/1220 rev, or 1220 rev 3, where you can get this document. On Tuesday, we did chapter 16 review. So now we'll do chapter 17, which is a lot longer. I wasn't able to finish at the 8 a.m., so I'm gonna skip around. But chapter 17 has, I like to think, 3 main ideas: buffers, titrations, and then KSP. So I don't know which one's the hardest: buffers, titrations. So I'm gonna, I put together this document to kind of address some, I guess, misconceptions I've been seeing a lot. That's the point of these packets, is one, not only to drill and kill, so you can kill it on the exam on Friday, but to address some of these misconceptions, so when you study, you'll be more successful. Okay, so one of those things that I've seen, and I mentioned this at the review session on Tuesday, is that, yes, in chapter 17, we learned about the Henderson-Hasselbalch equation. Y'all love to just shove any numbers into the Henderson-Hasselbalch equation, regardless if it's a buffer or not. You can only use the Henderson-Hasselbalch if it's a buffer. We only have a buffer when we meet very specific criteria. So this slide is meant to test you. Is this a buffer or not, and is this an appropriate use of the Henderson-Hasselbalch equation? Because if you use the Henderson-Hasselbalch equation for everything on the midterm, you will get 80% of them wrong, all right? A buffer is only produced, like I know on the supplemental information, we give you pH equals pKa plus log base over acid, okay? This is misleading because I just say base over acid. Can it be any base? Can it be any acid? No, it has to be an acid-base conjugate pair. My mouth is lazy and I just say base over acid, but what I actually mean is weak base and its weak acid. That's what I actually mean. So base over acid means I need actual mole amounts of F minus and HA, or HF. Mole amounts, molarities, it doesn't matter, right? I can only put those substances into the base to acid ratio. I can't put sodium hydroxide, I can't put HCl. Has to be F minus and HF. Or it can be ammonia and ammonium. Something like that, okay? Has to be an acid and its weak base, all right? If you don't have those, if you don't actually have numbers to put in that base to acid ratio, then you cannot use the Henderson-Hasselbalch, and there's a different way to calculate the pH for that. Okay, so tell me, I'm giving you numbers. Tell me, is this an appropriate use of the Henderson-Hasselbalch? I'm just giving you the base to acid ratio. We already know the pKa's. So here, if I have 1 molarity NaF and HF, can I use the Henderson-Hasselbalch? Yes, I can. Yes, because look, there's F minus, there's the base, there's the acid. Molarities are fine. So if both of those are in solution, yep, yeah, just go to town, go put it in the Henderson-Hasselbalch. All right, the next one. Ammonia, so 1 molarity ammonia and ammonium chloride. Is that allowed? Yes, it is. Because there's the base, there's its conjugate acid, ammonium. Perfect. All right, so those were molarities. What about this? What if I do 1 millimole of NaF and 5 millimoles of HF? Is that allowed? Yes, that is also allowed, because a molarity ratio is the same as the mole ratio because the volumes are the same. All right? If both of these are in 1 liter, then you divide by 1 liter on both the top and the bottom, they cancel out. So that one's cool too, because NaF is the base, HF is the acid, the conjugate acid. All right, the next one, 5 millimoles of ammonia, 1 millimole of HCl. Is that an appropriate use of the, no, it's not. But Dr. N, ammonia, that's a base and HCl is an acid. Why can't I put that in the base to acid ratio? What's wrong? Yes, HCl is not the conjugate. So we cannot, this base to acid ratio is not 5 to 1. But is this a buffer? Maybe. So let's take a deeper look at this. If you mix 5 millimoles of NH3 and 1 millimole of HCl, ammonia is a base, HCl is an acid. If you combine one of each of those, that's how you make the conjugate acid. So if you combine like 1 unit of ammonia, 1 unit of the strong acid HCl, that is how you get ammonium. There is the conjugate acid. So the question is, when you mix these things together, is it a buffer? It actually is, it's just the base to acid ratio is wrong, right? So just do like a lazy BCA table here. You are combining 5 millimoles of ammonia, 1 millimole of HCl. So when those two things react, what is in your afterline? How much ammonia do you have left? 4, 0 HCl, and what? 1 ammonium. These are the numbers you put in your base to acid ratio. So it is not 5/1. This is still a buffer, but the actual ratio is 4/1. You have to do a BCA table first because you're adding like a strong acid or base. You're making a buffer via partial neutralization. All right, let's keep going. E, is that a buffer? No, heck no. Why is it not a buffer? It's 2 strongs. How would you calculate the pH of this? If you have 5 millimoles of base, strong base, 1 millimole of HCl, those two things neutralize one another, all right? So when those two things react, what is left over? 4 millimoles of what? NaOH. So in your head, because I made the numbers easy, you actually did a BCA table, all right? In your head, you did a BCA table. So if 4 millimoles of sodium hydroxide are left over, if you divide by volume, that's how you get concentration of sodium hydroxide. You just go ahead and calculate pOH. That is just excess strong base. That is not a buffer. Okay, it's not a buffer, so don't use the Henderson-Hasselbalch. All right, next one. 0 millimoles of NaF and 1 millimole of HF. Why is it not a buffer? There's no NaF present. Yeah, so you can't use the Henderson-Hasselbalch. It's not a buffer. So if the only thing in your solution is HF, do you know how to calculate the pH of that? Yeah. Yeah, that was from chapter 16. That's x squared over initial concentration equals Ka, right? This is not a buffer. There is no conjugate base present. This is like the beginning of your titration. I know when you think titration curve, you think Henderson-Hasselbalch, but you only use the Henderson-Hasselbalch in very one small region of that titration curve. In the other points, you do something completely different. And F is an example of that. So that is not a buffer. This one, G, is this an appropriate use of the Henderson-Hasselbalch? It is not. So after these two things mix, what is left over? 1 millimole of HCl And you've converted all of that F minus to HF, right, after neutralization. So you've overshot your endpoint. You've already neutralized all your base to its conjugate acid, but you also have a strong acid HCl left over. So how do you calculate the pH of that? HCl is an acid. HF is an acid. You pick the strong one, so you assume that HCl is the only thing there, all right? And then you just, I actually have to give you volumes. I didn't give you actually any volumes. The concentration of HCl that's in excess will give you your pH. You're going to pretend that that HF isn't even there, right? So only a handful of these were actually buffers. You got to think, knowing where you are on the titration curve helps, and so I'll point that out, right? Again, in order to use the Henderson-Hasselbalch, you actually have to have numbers in this base to acid ratio. It can't be 0. No zeros. That's somewhere else on that titration curve. Let me show you this graph, all right? Here is a titration curve where at the beginning of your titration, that's HA. That's not a buffer. It's only your acid is present. So you just do x squared over initial concentration equals Ka. At your equivalence point, you've converted all that HA to A minus. A minus is a base. So you use Kb equals x squared over whatever, initial concentration, or whatever, that diluted solution is. Have I used the Henderson-Hasselbalch equation yet? I have not. There's only one place you do the Henderson-Hasselbalch, and that is volumes between your beginning of your titration and the equivalence point. That is the only place you use the Henderson-Hasselbalch. And the reason is because in all of those volumes, you have both a mixture of HA, because you haven't reacted all of it yet, you haven't neutralized it all yet, but you have converted some of it to A minus. So you actually have both. You have actual numbers to put in that base to acid ratio. Everywhere after the equivalence point, this is excess hydroxide. Excess hydroxide. So if you know where your equivalence point volume is, if you're before it, yes, it's a buffer, but if you're after it, it's excess hydroxide. All right. So I hope that clarifies things. Be very cognizant of what you are combining together. You need actual numbers to put in that base to acid ratio. So I made it easy here where I just gave you the mole amounts you were mixing. So let me make it harder. Tell me, is this a buffer? Should you, if you mix these two things, use the Henderson-Hasselbalch equation? You may or may not. So we have to decide. You actually have to get millimole amounts of all of these things. So we have to do that. So I have 100 millimoles of ammonia. And what is this? 100 millimoles of, what is this? NH4 plus. So would it be an appropriate use of the Henderson-Hasselbalch here? Yes, because there is your base, there is your conjugate acid. So we will use our Henderson-Hasselbalch equation where our base to acid ratio is 100 over 100. Perfect. Okay, next one. HF, so this looks like it's 100 millimoles of HF. How many millimoles of this thing? Also 100 millimoles of NaF, so this is F minus. Do I use the Henderson-Hasselbalch? Yes, I do. I use the Henderson-Hasselbalch. What is my base to acid ratio? It's also 100 over 100, so it's 1. Okay, so these two things, yes, I use the Henderson-Hasselbalch. Perfect. These are type 1 buffers. You are literally just putting the acid and its conjugate base in directly. No need to do a BCA table. What about the next one? HF. Oh, but this time I'm not adding NaF. What am I adding? Sodium hydroxide. So I have to do a BCA table first to decide, do I have a buffer or not? So we are combining 100 millimoles of HF. And then what is this? 50 millimoles of not F minus, but sodium hydroxide. Know that at least 50% of your classmates will just shove those numbers in the Henderson-Hasselbalch equation and just put 50 over 100. But you know not to do that, right? You know why they want to do it. They just see, oh, sodium hydroxide 50, acid 100, and they do 50 over 100. But that is not the base to acid ratio. What do we have to do first before we plug into the Henderson-Hasselbalch? A BCA table. Can you do it in your head? Can you tell me, after you mix these two things together, how much HF do you have left over? 50, and then how much F minus did you make? 50. So your base to acid ratio is actually 50 over 50. It's 1. It is not 50 over 100. Remember, base to acid ratio, it's not any base, it's not any acid, it has to be the base and its conjugate acid, or acid and its conjugate base. All right, next one. These two things, so 100 milliliters or 100 millimoles of HF, and this is 100 milliliters or millimoles of sodium hydroxide. Oh, so is my base to acid ratio 100 and 100? Nope, it is not. You're adding a strong base, so these two things neutralize one another. You got to do your BCA table first. So hopefully you can do this in your head. What is in my after line for this BCA table? How much HF do I have left? 0. What did it all become? F minus. I have 100 millimoles of that. Do you know how to calculate the pH of that? Yes, if you have the volume, I think it's 200 milliliters. Use KB equals x squared over whatever gives you POH. That, did I use the Henderson-Hasselbalch? No, I didn't. That's just a KB. It's just a weak base. That's the only thing in water because you're at the equivalence point. You're no longer in the buffer region. Okay, next one. Ammonia and HCl. So I am combining 100 millimoles of ammonia and 60 millimoles of HCl. So is my base to acid ratio 100 over 60? No. What is it? It is 40 over 60, yeah. So I'll write that out. These two things react. Weak base reacts with that strong acid. 60 milliliter or 60 millimoles of HCl will make 60 millimoles of the conjugate acid, and you are left over with 40 millimoles of ammonia. And so that's why my base to acid ratio is 40 over 60. Okay, so BCA first, then Henderson-Hasselbalch. All right, last one. Oh no, we got two more. Okay, ammonia and 0 milliliters of HCl. Is that a buffer? Heck no. How would you calculate the pH? KB, yes. So this is not a buffer at all. So the last one was a buffer. This one is KB equals x squared over 1. Get the pOH. You haven't added any acid. The only thing present is ammonia. So if you think about it, right, try with all your might to make a base to acid ratio. What would it be? Well, it would be divided by, what number would you divide by? 0. Are you allowed to do that? No, the math people, they'll yell at you. So that's why you don't use the Henderson-Hasselbalch, because you're dividing by 0, so it's obviously not a buffer. You have to calculate it a different way. In this case, you use KB. All right, last one. 100 milliliters of ammonia and 105 milliliters of HCl. So do your BCA table first to figure out if you have a buffer or not. So we're combining 100 millimoles of ammonia and what is this? 105 millimoles of HCl. Is this a buffer? It is not. So after you combine these things, you will convert all of that ammonia to ammonium. But then you also have something that's in excess, and what is that? How much HCl? 5 millimoles of HCl. So how do you calculate the pH of this mixture? Ammonium is a what? Acid. HCl is a acid, but which one do we care about? HCl. So all you have to do is just figure out, okay, what's the concentration of HCl? Get the pH, that's it. This is after your equivalence point. right? So you're no longer in that buffer region. It's the excess strong thing dictates your pH, right? So I hope this highlights just because we mix two things together doesn't always mean it's a buffer. You really have to inspect what is in your solution. Do you have large amounts of the acid in its conjugate base? If so, then yes, it's a buffer. If you just have a weak acid, use Ka. If you just have a weak base, use Kb. If you have excess of a strong thing, that strong thing is what dictates your pH. All right, so I hope that helps. Okay. All right, let's do this one. All right. HL is a weak acid. There's its Ka. How many milliliters of Kl should be added to HL to make a buffer with a pH of 4? So HL is your weak acid. That's essentially HA. What am I adding to this solution? What is Kl? It's its conjugate base. Kl is K plus and L minus. So you are directly adding that conjugate base. So this question is a little bit backwards. I give you the pH. I want you to tell me basically what is that base to acid ratio. So the idea here is, well, let me ask, am I allowed to use the Henderson-Hasselbalch here? Yes, why? I literally tell you it's a buffer. I tell you it's a buffer, so you are allowed to use the Henderson-Hasselbalch. So pH equals pKa plus log base over acid. I tell you the pH, I tell you the pKa. pKa is, can you do that in your head? 5, yes, it's 5. I can calculate what is the necessary base to acid ratio I need to achieve this pH. So pH I want is 4, but the pKa is 5 plus log base over acid. I think I can do this in my head. -1 equals log base over acid. To undo a log, you take both sides to the 10 to the, so 10 to the -1 is 1/10. So base over acid equals 1/10. So what this means, so in your calculator, you'll get something like 0.1, right, or 1/10, meaning that for every 1 unit of base, you need 10 units of acid. Right, that's the base to acid ratio you need. And again, I'm being lazy, right? I'm just saying base over acid. Let's be hyper specific. That ratio is actually how many millimoles of L minus you need over how much HL you need. The weak acid and its conjugate base. That's the ratio I need. It can't just be any acid and any base. It has to be the acid and its conjugate base. So using the last piece of information we didn't use yet, I tell you that our solution starts with 100 millimoles of HL. So I know the denominator. I just need to calculate how much of that numerator I need. And that's exactly what I'm trying to calculate here. So how many millimoles of Kl do I need? 10, if you solve for that. All right, so equals, 100 over the base that you need, so just solve for that. And you need 10 millimoles of Kl to make this buffer, so that the base to acid ratio is 1/10. All right, that's not the answer. It says how many milliliters. This is a 1 molarity solution, so I think that's 10 milliliters. All right, bring it home. All right, so in this example, I can just, there's no BCA table necessary, because I'm not adding a strong acid or strong base. I'm adding the weak acid and its conjugate directly. So I can just put those numbers straight into the Henderson-Hasselbalch equation. No neutralization required because there's no strong thing. That's what the next question is. So see how I literally changed 2 letters. Instead of adding the conjugate base, like I did in the previous example, I'm actually adding a strong base. So this question you arrange a little bit differently. You actually have to do a BCA table first. But I'm actually going to skip this one because I want to do more KSP stuff at the end. So here in this one, you do have to do a BCA table first, then plug in that base to acid ratio for your Henderson-Hasselbalch. Our base to acid ratio is still 1/10. You just solve it a little bit differently. All right. Okay. Let's, do this one. Okay. Okay. So we have a buffer that is 100 milliliters of buffer, and it's two things. It contains 1 molarity of HR, which is an acid, and 1 molarity of Kr, which is its conjugate base. I tell you the pKa is 4, and I tell you that the initial pH of this buffer is 4 because the base to acid ratio is 1. Do you agree with that? Yeah, all right, perfect. Okay, so this buffer, as it's made, equal amounts of acid and base, pH is 4. I did this in the review. I'm going to change this to sodium hydroxide instead. Right? Let's add, and instead of 1 milliliter, let's add 10 milliliters for fun. Okay, just change it a little bit. Let's add 10 milliliters of strong base to this buffer. What does your intuition say happens to the pH? It should go up. Okay. So let's calculate it. So we already have a buffer and we're adding a strong base. So we have to do a BCA table. It's just a little bit different than before because we're already starting at a buffer. So the idea here is that strong bases react with acids. So I'm going to write the BCA table this way. You take the acid, HR, you add a strong base. What do you get? What comes out of here? R minus, and water, but we just forget about that, right? That's the reaction that's happening. You neutralize some of that weak acid to make the conjugate base. So we're going to do our BCA table, but the only difference here is that we just have values, beginning values for both of your acid and conjugate base. So we actually have to calculate how many millimoles of the acid do I have? 100. And then how many millimoles of the conjugate base do I have? 100. So I'm already starting with 100 of each, millimoles of each. How many millimoles of strong base am I adding? 10. Okay. So consume the limiting reactant to its entirety, right? So all 10 millimoles of that strong base react, so you have 0. But at the same time, you consume some of that acid, produce more of that base. So now you've converted some of that weak acid, where now you only have 90 millimoles of the acid. So I won't put A, I'll put HR. And now you have 110 millimoles of R minus. So see how adding that strong base just converted some of that weak acid to the weak base. You just changed the ratio a little bit. Am I allowed to put these numbers in the Henderson-Hasselbalch? Yes, because I have values for both of them. So when you do that, your base to acid ratio is 110 over 90. So pH equals what? 4. pKa is 4 plus log 110 over 90. Let's do that. So log 110 over 90 plus 4. I get a pH is 4.1. So we added base. Did the pH go up? Yes, but it went up because all we did was change that base to acid ratio, just a little bit. All right. Okay. So with that in mind, this is how a buffer resists pH changes with strong acid or strong base. Right? If I would have changed this to acid, let's say we added HCl, instead of the base to acid ratio being 110 over 90, it would be 90 over 110. That you're just shifting, you're making the different conjugate, essentially, right? So what we see is that base to acid ratio really depends on what those beginning values of your buffer are. So with that in mind, which buffer is more resistant to pH changes? Right? So why did the pH change? It's because the base to acid ratio changed. So in which scenario does that base to acid ratio change less? A, or B? A, where we have 100 milliliters of the buffer, or 50 milliliters of the buffer? What do we think? A, yes. It is A, because if you get millimole amounts of both of these, it's 100 over 100. Versus in the other one, it's 50 over 50. So if you think about how the base to acid ratio changes when you add a strong acid, I know it's going to be like, -1 plus 1 on the denominator and numerator here. So we see that there's a bigger change for B because there's literally just less moles of stuff. So we see that ratio change a lot more, right? Okay, versus this one, what if we have same volume of each, but the concentrations are different? Which one resists pH changes more? The concentrated one. Again, because there's literally more moles to accommodate small additions of strong acid. This one is 100 over 100, but the bottom one is what? 10 over 10? Yeah. So if you add 1 millimole to each of these, 1 millimole of acid, this bottom one, that ratio is going to change much more drastically because those numbers are smaller. So that's conceptually. You might have just memorized earlier in that chapter, I just said more concentrated, more resistant to pH changes, and you just believed me. This is the mathematical proof why higher concentrations are more resistant to pH changes, because the numbers in the base to acid ratio are larger. So if you add 1 millimole of acid, 99 over 101 barely changes away from 1. But if you add 1 millimole to this one, it changes a lot more drastically. Okay, so let's do some more concepts. Because what do we like? Do we like the math or the concepts? Or what do we want to work on? Concepts, yes. I was thinking about making an all-concept exam. No calculator. Wouldn't that be fun? Wouldn't that be a fun practice exam to have? Yes. But here's the thing. It's really hard to write conceptual questions. Okay, all right. But I'll try. Okay, what is being titrated? What is in our burette? In the burette, the thing that we're dropping. We're dropping what? Are we dropping acid or dropping base? Base. How do we know? Goes up. So this is volume of sodium hydroxide. Okay, so look at our options. Which ones can we eliminate? Is it ammonia being titrated with sodium hydroxide? No. How do we know? Because this beginning thing has to be a acid. All right. So that's what we have here. So we can actually eliminate E as well because we don't want HCl in here. It has to be a base. So the question is HCl in our Erlenmeyer flask or is HF in our Erlenmeyer? It is HF because HCl and sodium hydroxide, that is a strong acid, strong base neutralization. From this picture, you clearly see a buffer region. Will a strong acid, strong base ever make a buffer? It will not. A strong acid, strong base neutralization looks like this. It's acidic, 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 basic, 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 and that's it. There's no buffer region. See how there's this little swoop at the beginning? Because you start with all acid, now you have a buffer, 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 buffer. Then you make your, you do your equivalence point and then your base. So this is a strong acid, strong base. No buffer region, it's just like flat. So that's why the answer is D. Here, that looks like that. Here, C, this is not even a titration. You are adding a weak acid and its conjugate. It's not a titration, you're just making a buffer. All right, so that one is kind of the odd one out. Okay, so true or false? And please make me proud. All right. Is the pH of this titration at the equivalence point 7? Yes or no? No, it's not. Very good. Very good. So if you titrate HF and sodium hydroxide, the equivalence point pH is not 7. What is it? It is greater than 7. Why is it greater than 7? Because you make F minus. At the equivalence point, F minus is what's present. At the beginning, it's just HA or HF, whatever. then at the equivalence point, you just have F minus. F minus is a base, so your pH is going to be basic, all right? For what kind of titration is pH 7? Just strong acid, strong base. So in this one, yes, you can say for certain that the pH is 7. If you ever take an advanced class with me, you'll learn that it's actually not 7. But for this class, it's 7. Okay, here's my redemption slide. Okay. Based upon the information you just told me. You just told me at the equivalence point between HF and sodium hydroxide. What is it? It's what pH? Basic, yes. Which indicator should we use? Methyl red, bromothymol blue, or phenolphthalein? So that means we can ignore many of these. We can ignore all of these. We're just looking at these three. So this graph is in your textbook, and how they present the color change is they're just showing you the sliver in which the color change occurs in order to allow you to focus on where that color change happens, right? So the important thing here, and I think this was, I did a poor job, I'm sorry, for exam 3 or whatever, or 2, explaining that I didn't explicitly say that, oh, these colors are forecasted, they extend beyond what is just listed. You should have observed this with phenolphthalein. You've used phenolphthalein so many times, haven't you? When it's acidic, it's colorless, even though on the graph it doesn't necessarily say that. As long as it's basic, it is pink or magenta pink, even though the graph doesn't necessarily show it in those regions. So we have to recognize that it extends past those pHs. So that's how our textbook shows it, just because they want you to focus on where that color change happens. So I went on the internet to find a different chart. It's the same thing, but it's a little messier because they show all the color regions. So here, if you look at phenolphthalein, right around pH 8, everything above 8 is hot pink, but everything below 8 is colorless. So see how that color is extending. But in our chart, the other one up there, it's just focusing in on where those color changes are happening. All right, so that's how we read the chart. Okay, so based upon that, so now that you know how to read the chart, which indicator should we use to catch the equivalence point of this HF sodium hydroxide titration? Phenolphthalein. Why phenolphthalein? Because the color change happens in the basic region. Because if we use methyl red, the color change is going to happen way before the equivalence point. The idea is we want to catch the volume in which this, F minus is produced, and we know that this range is in the basic regime. And so if we get an indicator that changes color in the basic regime, we can be confident that we caught that equivalence point. Yeah?
Titrations that aren't strong and strong, how basic or acidic does it get?
Wait, hold on. Well, that's not strong or strong.
Yeah.
So if you had like a weak acid and a strong base?
Yeah, like how basic how acidic would it be at the equivalence?
Just a little basic. It's not going to be like 14.
Yeah, but does that mean a little?
So,
10.1?
well, here's the thing. So yes, I know that this dot is basic, but the volume difference between here and here is like a drop. Remember when you did like the LLT experiment and you did the titration? The difference between light pink and hot pink was what? Was it a big volume? No, it was a quarter of a drop, because your pH changes drastically in a very, very small pH range. So as long as your indicator changes color somewhere in this range, you could kind of be at the top end or even the low end, that will still be a great indicator to use. Does that make, because it's a range. Does that make sense?
Okay. It looks like I think it was bromothymol blue or whatever. It looked like that one, I feel like you could use it.
Oh, no, yeah. Yes, well, here's the thing. Bromothymol blue, I think the color change happens around 7. And to me, that's a little too early. Because 7 is neutral, right? You don't want the pH to change when it's pH 7. You want it to change when it's a little bit more basic than pH 7. So that's why bromothymol blue isn't a good indicator. But would bromothymol blue be a good indicator between an HCl sodium hydroxide? It would be, because what's special about that titration? The pH is 7 at the equivalence point. So the question is, why didn't we give you bromothymol blue for those strong acid, strong base titrations? It's because it's really freaking expensive, right? So we just use phenolphthalein because we recognize in a strong acid, strong base titration, yes, the equivalence point is 7, but if, you know, if phenolphthalein changes color around right here, and the difference between this volume and this volume is 1/4 of a drop, who cares? It's close enough. That's why we always said, you know, it's the first drop that makes it change. Because if you go a little bit past, then yeah, you definitely went past your endpoint. Does that help? Okay, yes. Yes, if we lived in a perfect world where money wasn't an issue, we would pick bromothymol blue, but it's not necessary. Okay, so we got 15 minutes. So let's do some molar solubility stuff, then I'll do my demo. All right. So this is KSP stuff. KSP hopefully is easier because you're just using a K expression that has nothing in the denominator. So when we ask you for molar solubility, in your head, know that that means X in the ice table. Molar solubility is X. KSP is the solubility product, the solubility product constant, and that's a constant. But molar solubility can change. So here we are just calculating what is the molar solubility of these things in pure water. These are simply, you write out your KSP expression, so we have our solid. It breaks up into 2 units of the A cation, 3 units of the X anion. Okay, I'm not worried about charges or anything. What's important is the ice table. Since we're dissolving this in pure water, we are starting with 0 of the products. It's pure water. There's literally, it's unadulterated, nothing's in it. Throw in a chunk of your solid, a little bit of it dissolves, so you lose an X amount of the solid. How much of the cation do you gain? 2X. And then you gain 3X of your anion. So at equilibrium, you have N minus X of your solid, 2X of your cation, 3X of your anion. This is why X is molar solubility. Think about what this means. Molar solubility is the amount of solid you lose when you dissolve your solid in 1 liter of water. So N minus X, that's how much you're losing to the actual solution. But what we see, yeah, we're solving for X, but we don't need N minus X in our KSP. And so I skipped a step. I didn't actually write what is the KSP expression. Just like all KSP expressions back from chapter 15. We've been talking about K for so long. It's concentrations of things, right? So the KSP, or the K for this reaction, is you take the products, the concentration of the products. So A, so this is actually A3 plus, but whatever, to the second power, because there's a 2 coefficient, times X concentration to the third power. So remember back in chapter 15 when we did K expressions, the only place that those coefficients showed up were the exponents. So do not try to put 2s and 3s in these values in just the normal KSP expressions when we use concentrations. So then the question is, well, how do we get molar solubility? Now we take this KSP expression and now we put the 2X and the 3X in it. So there's a difference between these 2 expressions. So KSP equals 2X squared, 3X cubed. So when we do like 2X squared or 3X cubed or whatever, that's when we put things in terms of molar solubility. X is molar solubility. So we know what KSP is, solve for X, you get an answer. That is the molar solubility of this solid, is when you solve for X. So in the follow-up question is the same thing except backwards. I give you the molar solubility. I'm asking you what KSP is. So I am telling you that X is equal to 0.01 molarity. So you need to figure out what is the KSP expression in terms of molar solubility. So if this is AX3, KSP is equal to A concentration times X concentration cubed. But is this in terms of molar solubility yet? It is not. I need to put it in terms of X. So when I dissolve this salt, how much cation do I make in terms of X? 1X, yes. Then how much anion do I get? 3X. So now I put this in terms of molar solubility. It's X times 3X cubed. I know what X is, plug it in, and then that's how you get KSP, right? Molar solubility is X. It is different from your just plain old KSP expression with concentrations, right? Students often mix those up. Okay. Okay, consider, so in these examples, I dissolved salts in pure water. Here, I'm mixing together two, a cation and anion, and I want you to predict, will a precipitate form or not? So no, I am not using molar solubilities here. I just give you concentrations. So simply just use the KSP expression, right? I tell you that the KSP for MX2 is 10 to the negative 4. So this is equal to M concentration times X concentration squared. That's what KSP is, right? But these are just kind of random concentrations. So use the KSP expression and calculate Q. So Q, in this case, use that KSP expression, is 0.1 times 0.1 squared. Use the concentrations that are given. Because I give you concentration. I'm not giving you molar solubility, so you're not plugging in X. You're just plugging in these values straight into KSP. And I think I know this. This is 1 times 10 to the negative 3 is Q. So tell me, which one's larger, K or Q? Q. So does a precipitate form? Yes, it does. Perfect. So let's do one more. This one, this is a different substance, different KSP. So get that expression. We have N concentration, X concentration, but it's cubed. So you're just putting in those values. No X's, no molar solubilities. So I think, what is this? 3, 4, 1 times 10 to the negative 4 is Q. It's bigger, yes. So that does a precipitate form, yes. So if it's less than, if Q is less than K, a precipitate does not form. Okay. All right, I have a few minutes. Okay, so in this example, in this example, the first one up here with molar solubility, we dissolved junk in pure water. So since it's pure water, the initial lines of the ions are 0, since it's pure water. It's different here. Consider this compound, so it's MX2 again, or whatever, but this time, I don't want to dissolve it in pure water. I want to dissolve it in a solution that is already 0.1 molarity M2+. So up here, I'm just telling you what X would be if it was pure water, but now I don't want you to calculate what is the molar solubility in pure water. What is it in this solution? So our strategy is actually the exact same. Dissolve your thing in water, so M2 plus 2X, that's KSP. But this time in our ice table, yeah, we throw in a chunk of my solid, but in my initial line, these aren't both zeros. When it was pure water, they were both zeros. Now, I'm already starting with 0.1 molarity M2+. But you can still predict, which way does this reaction have to go? It has to go forward, yeah, so minus X plus 2X. So at equilibrium, it's N minus X, 0.1 plus X, and then 2X, right? KSP is equal to M concentration, X concentration squared. So putting in those numbers, 0.1 plus X times 2X squared equals the KSP it's given, 10 times 1 times 10 to the negative 8, right? So this, as written, is a quadratic. Do you want to do the quadratic? No. So let's get rid of that plus x, because I know that number is going to be really small. It's going to be really small, right? So then simply, you solve for this and you get x. And remember, do we want to calculate x? We do, because this question is asking for molar solubility, and that is x. So solve for x, you're going to see x as a really small number compared to the regular x when it was pure water, right? And what this demonstrates is the common ion effect. Things are more soluble in pure water than a solution that has a common ion. So here are the 3 factors that affect solubility. Really what it is disruption of the KSP expression. Really, you're just utilizing, Le Chatelier's principle. But if you just want to memorize these different factors, hold on, I just want to go down here. All right, the three different factors. Common ion effect will decrease molar solubility. Note how I said x. Did I say KSP decreases? No. Does KSP ever decrease? No, because what is KSP? It's a equilibrium constant. KSP does not change. It's x that is changing. pH dependence increases molar solubility, but only for some things that are bases already. And then complex ion also increases solubility, right, for a similar reason. So I have 2 demos up here, so I'll end here, do the demos, and we'll predict what happens here. So the reason molar solubility changes for these things is because we're just disrupting our equilibrium a little bit, right? So let's do the first one, common ion. So I have, oh, I don't want these. I have a saturated solution of NaCl right here. Okay? It's a saturated solution of NaCl. So let's remember Le Chatelier's principle. If we add a product, which way does the equilibrium shift? To the left. So what do our eyeballs observe? What should we see? Solid form. So we see X gets what? Smaller. It gets less soluble when there's a lot of a common ion present. So what I have right here is a saturated solution of NaCl, but there's very, very small amount of solid present in it. And so what I'm going to add is HCl. I'm going to add HCl to this solution. And so adding HCl is adding which common ion? Chloride, yes. I know it's an acid, but it's just an easy way to add chloride all at once. So we'll see what happens here. I should probably use gloves. It's conch acid. I didn't do it for my last class. I had to like wash my hands. Okay, so I'm going to add HCl. So what should our eyeball see? We should see a solid form, yes, because we're pushing the reaction backwards. So let's see. Oh no. Oh man, sometimes it works, sometimes it doesn't. If they don't make it fresh, sometimes it doesn't work. Dang it. Okay, there we go, right? You see a little bit of solid form, okay? That it's all murky, that's some of the solid being formed because we're adding HCl. Usually it's more drastic than that. HCl. That's how we can get more solid to precipitate out. Okay, let's do this other one. Okay, so complex ion, or common ion effect decreases molar solubility. pH dependence. So the idea is, okay, if we add a product, the reaction shifts backwards. But if we remove a product, the reaction shifts forward. So X increases. So the way we can remove a product is by getting acid to react with something like a base, like hydroxide. So I have a solution of magnesium 2+. I'm going to add base to it, right? So right now this just has magnesium 2+ in it, so it's not a saturated solution yet. So I'm going to make it a saturated solution by adding some base to it. All right? And so if we have a saturated solution, what should it look like? Does that look like a saturated solution? Yeah, because there's like solid present, all right? So there's some solid present. So right now I have that chemical equilibria established. But now, so I added base, so I have magnesium hydroxide. Now I'm going to add some acid. So acid is going to react with which substance in that chemical equilibria? The OH minus. What is it going to do? Add it or remove hydroxide? Remove it. So which way should the equilibrium shift? Okay, and what should we observe? We should see the solid do what? Come on, go, go, go. You did it last time. What happened? Oh my gosh, yeah, it got less murky. Now it's colorless again because we added acid. The solubility of that solid increased. All right. Thanks for sticking around. If you come to office hours, we can finish this packet.